Yeah, so let's take a look at a couple of examples from chapter 7. Let's work out a couple problems. So the first one is this 719. So we've got a distributed load here underneath some beam, and that's held up by a pin at point A and a rope at point B, and they want us to find the internal forces at pin C. So if you remember the process, you need to find if you need the external reaction forces, and you will because you notice A and C are kind of connected together at that point. And if you use the other side, you're going to have that B with the pulley, so it's probably easier to use A and C. So we need those reaction forces at A and C. I'm going to show you two ways that I did this problem. I'll show you first the way the book did it, and then I'll show you my way, which I have a little bit of a slight shortcut to my way. So they start off with the entire beam and they find the external reaction forces. So they want to find that tension, which is that thing at B. So they take a moment at A to get rid of the AX and the AY, and they write a moment equation at B to find the tension, which you can see there. All right, so then they take that information, they sum the forces in the X direction. So you've got that tension in one direction, the X direction, you get the AX in the other direction. So of course, they're going to be equal to each other. And then they find the sum of the forces in the Y direction, and you have the distributed load made into a point load pulling down, and AY going up. So that gives you your your AY value. So that's how the book did it. Well, of course, wait a minute, could actually do the problem, right? So they apply that to the AX and the AY, taking that segment, and of course they're drawing the VC, the moment at C, and the normal force at C, and so they solve by applying the equations of equilibrium. So the force, sum of the forces in the X direction, we find the NC equal to the Fx. We sum the forces in the y direction, and we find the Vc, the shear force, equal to F, between the two forces that are being pulled down. Oh, important thing to remember here. The distributed load acts across the entire beam, so there still is a distributed load acting across this 3 feet. That's what that 8.45, or not 8.5, it's 0.45, gotta get my eyes checked, kip pulling down is. So the combination of those two is VC. And then of course they did a moment at point C. Remember, your free moments don't cancel out. So you've got MC, and then you have your forces that are acting. So you've got your 1.8 kips and your 0.45 kips. Those are creating a moment at point C. They solve that, and they get the moment at point C. Fine and dandy. So when I did this problem, I decided to kind of take a slight shortcut. So instead of doing a moment at point A, I don't really care about that tension, right? That whole piece I'm going to drop out. So I sum my moment at point B. When I sum my moment at point B, AY goes through point B, but AX creates a moment at point B. And I have the distributed load piece that is also creating a moment. So those two things combined together, I get my AX, same value they got. I'll use positive convention, and if you get negative answers, you know that you assumed the wrong direction, of course. So I sum the forces in the y direction. I don't bother with the x direction because I already got the ax piece. Sum the forces in the y direction, and I get my ay component. So then I took those and applied them to my piece, right? So my piece looks remarkably similar to theirs. Strangely enough, it seems like I can read mine a little bit better than I could read theirs. So sum the forces in the x direction, and I got NC. I got a negative value. I assumed positive convention, so that means my NC force, right, is going in rather than coming out, right? VC, I got a positive answer by summing my forces in the y direction, so it is going down. MC, I got a positive answer, right? So that assumes that the way I've drawn it is correct. So there you go. There's my way versus the book way. I just took a slight shortcut. I don't know, I like to always find shortcuts when I'm doing problems. So there's one way to do the problem, right? So essentially the first part of chapter 7 is basically, here's a piece, take and cut that piece and boom, find out what the internal forces are at that point. You don't know for sure if that's the maximum forces or the minimum forces or somewhere in the middle at that point. It's kind of a bad, not really a bad, it's a bad overview of what's happening inside of the beam. It only tells you that one point. So the second part is actually creating shear, moment, and load diagrams. So in this particular case, we have a shaft, right? There's going to be a reaction force, of course, at point A and point B, and there is a load P applied to the shaft. So they want us to create a shear and moment diagram and load diagram by default for this shaft. So where do you start? Well, you start by finding your AX, your AY, and your BY reaction forces. One of those bearings, the one at the A side, was not meant to slide out. The one on the BY side was meant to slide through. So that's why there's just a normal force BY, and there's an AX and an AY. So I start with the whole thing. I sum for my reaction forces, right? If I sum the forces in the X direction, hopefully you can see that AX equals 0 at this point, right? So then I did a moment equation at point A, which allowed me to solve for BY. And then when I had BY and that force P, I summed the forces in the Y direction, sum equals 0, and I got my AY. So I redrew that down there in the bottom right-hand corner, right? That's the load diagram, right? There's 6 kilonewtons pushing up at AY. There's 9 kilonewtons pulling down at that load that's being applied. And there's 3 kilonewtons pushing up at BY. So if we integrate, right, if we have a constant and we integrate, we get a line, right? If we integrate a line, we get an x squared term, and if we integrate an x squared term, we get an x cubed term. So and if we have just a constant, right, and we integrate it, we get the line. So each one of these, as we move down from load to shear to moment, is the integral of the one before it. So if we look at shear, and actually the way that Dr. Hansen talks about these videos, he says, picture you're standing on a balance beam and you got a backpack on, right? So when you step on the balance beam, right, you'll see that 6 kilonewtons goes up. So as soon as you step on, 6 kilonewtons is taken out of your backpack, right? You walk along until the next point, you got that 9 kilonewtons coming down, right? That's 9 kilonewtons being loaded into your backpack. So you see the shear goes from 6, it goes down 9 at that trigger point. So it goes from 6 to -3, right? Continues along to -3 until we get to the end, right? And then that 3 is taken out and you get back to 0, what you started with. Always starts at 0, ends at 0. If it doesn't, you screwed up some force along the way, probably your reaction forces. All right, straight lines, right? So we went from points to straight lines. And that means now we're going to get slanted lines. So from the start to the trigger point there, you'll notice we have a positive area, which means we're going to have a positively sloped line. Right, the area underneath that curve, it's 6 high, 2 long, the area is 12. So we get a slanted line that starts from 0, climbs to 12 at the point where that 9 kilonewton force is. Right, so then if we look at the other piece, that other square rectangle, you'll see that in that particular case, right, it is 3 kilonewtons. And it's 4 long, so 3 times 4 again is 12. So we're going to get a line with a slope of 12. You notice it's negative area, right? It's below the origin. So we'll get a negative sloped line. So that's how we get the shear curve going down. So if we look at this, right, where do we have the maximum shear force? Well, between 0 and 2 meters, right, we've got a shear force of 6 kilonewtons, right? Where do we have the maximum moment, right? At the maximum moment is 12 kilonewton meters, right? And that happens at the 2 meter mark. So that is the second half of chapter 7. where you come up with your load, shear, and moment curves based upon the problems that you are given.